I'm going to be talking through the solution to question 3 in the 2015 examination paper for numerical methods for partial differential equations. So question 3 presents you with the shallow water equations, okay, written in vector form, and it's defined what the vectors u and f are. So u is a two-element vector. Element u1 is equal to h, which is the water height, and element u2 is the momentum, which is calculated by water height h multiplied by flow velocity u. Okay, f is another vector. F1 is the element of the momentum, which is h times u. F2 is hu squared plus half gh squared. F is normally known as the flux vector. And g in this case is 9.81 meters per second per second. Okay, question A gives you the Jacobian matrix and asks you to write the shallow water equations in quasi-linear form. So this is slight difference to the shallow water equations up here. Instead of the flux vector f, you've got the Jacobian multiplied by the vector u differentiating with respect to x. Okay, so what we really have to do here is we have to write the f1 and f2 terms using u1 and u2. So f1 is simple. F1 is equal to hu, where hu is also equal to u2. So f1 as slight typo there, that should say u2 by the way. F2 is hu squared plus half gh squared, so we need to get that from our u vector. Okay, so we do this by squaring hu to give us h squared u squared, and then dividing it by h. So that's u2 squared and divided by u1. And divide is achieved by raising u1 to the power minus 1. Half gh squared is simpler. We just say half times g times u1 squared. Okay, so now we need to calculate these partial derivatives in the Jacobian. So the derivative of f1 with respect to u1 is quite trivial, is 0. Derivative of f1 with respect to u2 is going to be 1, because we're differentiating u2 with respect to u2. Derivatives of f2 slightly more involved. Okay, so here we've got f2 written in terms of u, because we're differentiating with respect to u1. Okay, so we subtract 1 from that power and multiply that term by minus 1, and we multiply this term by 2, that gets rid of the half, and subtract 1 from the power. Once we also write it in terms of gh and u, because u1 is h and u2 is hu, this comes out of minus u squared plus gh. Okay, derivative of f2 with respect to u2, very similar, except for differentiating with respect to u2. So here we've got 2 times this first term, and subtract 1 from the power of u2. And we don't have any u2's in the second term, so that's just 0. So u2 is hu, divided by h, well obviously we could just give me u, or 2u in this case. Okay, so writing in quasi-linear form, all you do is you have the u vector, which is differentiated with respect to t, plus our Jacobian matrix, which we calculated the terms for up here, multiplied by the same u vector, but this time differentiated with respect to x. Okay, part B, find the Eigen Values of our Jacobian. Okay, this is just a 2 by 2 matrix, so it's quite easy to find the Eigen Values. If you want to do this using MATLAB, you can. Make sure you write down clearly what commands you used. Okay, it's not too difficult to do it by hand. So our Eigen Values are a solution to this quadratic here. So you use a quadratic formula, and you have 2 Eigen Values. So lambda 1 is u minus root gh, and lambda 2 is u plus root gh. Explain why the shallow water equations is a hyperbolic PDE. Well, since these eigenvalues are real, okay, because h is always positive and g is 9.81, so this square root is always going to be a real number. Okay, they're real and they're also distinct, i.e. they're not the same, so therefore the shallow water equations is a hyperbolic PDE. Part C, we're going to use the shallow water equations to model water flow in a one-dimensional channel. So the domain length is 3 meters, and we're only using 7 finite difference nodes at equally spaced intervals. The initial conditions are the height is going to be 1 when x is less than 1.5 meters, and the height is going to be a half where x is greater than 1.5 meters. and U, which is the velocity, is 0. So we're starting with completely still water. And we're going to be using the following finite difference scheme, which I haven't given you the name, but this is recognised as the Latch-Friedrich scheme. Okay, part 1, or part I, draw a diagram representing the grid for the problem. Diagrams often help to actually visualise a problem, so sometimes I quite often, when answering questions, just sketch out a diagram that helps me visualise the problem. Okay, so here's our domain. Okay, and we have 7 finite difference nodes. So these got 1, 2, 3, 4, 5, 6, 7. So our first node, which I've called node 0, is at the left-hand boundary at x equals 0. The last node, which is x6, the 6th node, well, I say 6th node, it's subscript 6, so we always start with subscript 0 for the first node. Okay, and that's at the right-hand boundary at x equals 3. Okay, because they're equally spaced, we can clearly see, well, it's not hard to see, but we have the spacing of a half. Okay, that's 3 divided by 6. We've also got ghost nodes outside. That's my minus 1th node, is that left-hand ghost node, which is at minus dx, or delta x, and we've got one at the right-hand side, which is node 7, or subscript 7, which is 3 plus dx. Okay, so given that the scheme is stable for a coordinate number of equal to 1, and the wave speeds of the fastest and slowest possible waves are u plus gh or u minus gh, calculate the maximum allowable time step. So the maximum allowable time step is your spatial step divided by what's the largest flow velocity possible given each node. Okay, so at the start, all your velocity is going to be 0, so we don't have to worry too much about this one. And then we just got root gh. Now we're looking for the largest value of h. Now if I just scroll to the problem, you can see either h is 1 or h is 0.5. So the largest value of h is going to be 1. So essentially we just got 0.5 over root g, which is 1.1596. And the third part, the final part of this question, calculate just one time step of the finite difference scheme using delta t is equal to 0.5, and giving the solution vectors for u2, u3, u4, and u5. Okay, so u2 is this node here. Okay, so we're going to be using, if I look at the scheme, okay, the Latch-Friedrich scheme uses nodes either side. Okay, so we've got ui minus 1, ui plus 1, fi plus 1, fi minus 1. So for this node here, I need the values either side at node 1 and node 3. Okay, so the x coordinate at node 1 and node 3, well, the x coordinate is 0.5 and 5. So because they're both less than or equal to 1.5, the height is going to be 1 at both of those nodes. Okay, so there we have the height. And because the velocity is 0, we've got 0 on the bottom. And delta t over 2 delta x, delta t was 1 over 2 root g. Okay, so that's where that comes from. So you can see for node 2, after we've done all that, the difference in fluxes is 0, so we have no change in our solution. For node 3, u4 has an x coordinate which is greater than 1.5, so therefore the height is going to be a half, so therefore we do have a change in the flux. Okay, and that's represented there. So after you do all the calculations, you get this value here. So we do have a change in the flux, so our momentum is going to change. U4, again, calculate that. Notice there's a subtraction missing there. That's just a typo. Okay, do something similar, and you'll notice after you've done all that, the solution for U4 is the same as the solution for U3. Okay, that's quite a common thing in the Latch-Friedrich scheme. If we move on to U5, okay, the heights at the 4th node and the 6th node are the same, so they're both falling half. So again, we've got no change in the flux. So that means there's no change in the solution for U.